Recording. Yep. So welcome to Sagar's presentation on a highly unusual topic, but also very interesting. Sagar, go ahead.
Yes. Yeah, thank you. Well, I'm very anxious to present all of you very smart people, but also very honored that you would join. Very excited to present this idea. As much as a very unusual idea. And so today we're going to talk about 1,000 brains and 1,000 chips. But first, we'll talk about transformers. They have completely taken over the world of AI in the last few years. Let me close this. And there's really been an explosion in the applicability of these models and breakthroughs, ranging from gold medal at the International Mathematical Olympiads and solving protein folding, for example. But despite these advances, current leading AI lack core attributes of biological intelligence. And such as, for example, rapid learning from limited data. It takes quite a few passes before a large language model can learn something. Continuous adaptation to new situation, like, for example, learning a new task that was not in the training data, and maybe changing input statistic. Learning while in deployments. So there's big cycles of training, and then the weight of the models are frozen, and you just infer. And there's also compute and energy efficient learning. These models take a lot of compute to both infer and train. Now, 1,000 brain systems, they're a new and emerging class of AI systems. And they're really trying to bridge the gap between artificial intelligence and biological intelligence. And so the way it works is you have, for example, this coffee cup here, and you have just a small patch of this image, and that's the input to your model. And then at every step that you get a patch, you generate a movement that will move the sensor in the environment, like this. And what these models are composed of is sensor modules, learning modules, and also a motor system. The very interesting thing is that these sensor modules, they don't just stream features to the learning modules, but they also always determine a location for these features. So over time, the learning module will not only have the features over time that are being sensed, but the features at specific locations. And as such, it can kind of create a graph over time of these objects. And what's interesting to us is that to scale these models, you basically add a lot of learning modules and sensor modules to the system. So an example of one of these systems, how it works, is basically as follows. So you have this very small patch here, which is the input to your system. And what the model does, it actually has learned models, and it tries to determine whether the observation that it's currently observing is consistent with its models, with its learned models. And as you can see here, it's pretty sure that the observation is consistent to being on the cup, like it could be on the cup. It's also pretty sure that it could be on this plate, but not as much. But there's no way it can be on this sphere. And after a few steps, the model gets more and more convinced of such things. It really has a strong sense that it's on the cup at this location, and less so for the bowl. And then after a lot of steps, all the evidence collapses into a single point. The model is sure that not only you are on this mug, but you are at this very specific location on the mug. And so these models, they really exhibit some features of biological learning, like, for example, rapid learning here. And basically, it takes a lot more training iterations for a visual transformer to reach the accuracy that it takes just one training epoch for 1,000 brain system. You also have continual learning. So this is a graph of the accuracy compared to the number of objects learned. And as the number of objects just grows, you see that the visual transformer's accuracy completely drops. It's forgotten the previous objects, whereas 1,000 brain system just retains this accuracy pretty high. You also have compute efficient learning, where it basically, to reach the same accuracy, it takes a lot less training, a lot less compute to train and infer these models compared to visual transformers. And one of the reasons why these models could be exhibiting such features of biological learning is because they are designed after biological systems. Like, for example, especially here at the learning module, because the learning module is designed after these things called cortical columns. And what cortical columns are, it's this thing in the human neocortex. the human neocortex it's basically composed of 20 billion neurons and 150 trillion synapses, and they're all arranged within these functional units called cortical columns. And you have about 200,000 of them in the human neocortex. And they kind of look like this. They're arranged in layers, and it's just a bunch of neurons. Now, to give a better idea of the scales of different biological systems, let's see this table here. So you have the human here, 200,000 cortical columns. You have the cat. It's like 100 times smaller, about 100 times smaller, with only 2,500 cortical columns. And you have the guinea pig, 400 cortical columns, and the mouse, 135. So the reason why I'm showing you this is because, well, if you really believe that these thousand brain systems have their learning modules designed after cortical columns, the motivation is very obvious to scale these systems to the sizes that we see here. And the question that we're going to answer in this thesis is basically, what are the consequences on computing system as we go up in scale? And the first thing I'm going to say to answer this question generally is that I'm going to go back to the setup we have. So it really is an interactive setup, because you get a sensory patch and you basically move it in your environment. And what you really have here is an autoregressive loop in disguise. We cannot really parallelize across the steps here. But what we can try to do is parallelize within a step. And this is very interesting here, because since we have so many learning modules, this represents an obvious parallelization opportunity. There's a lot of compute to be done, a lot of different memories here to be fetched. And so we investigate the scalability of thousand brain systems on GPUs, CPUs, and processing memory. So we use two different thousand brain systems. First one is Montyll. It was released in 2024. It's written in Python, and it builds models of the world using explicit graphs in 3D space. And this is basically what I showed before. And the other one is Montyll, which we introduced. It's a novel thousand brain system. And it's implemented using elements of low-level cortical processing, like, for example, accurate neural models. And the reason we designed it is to basically have a thousand brain system that was aligned with the long-term goals of the Thousand Brains project, and to really represent them computationally. So we start with GPUs. And what I'm going to say first is operational intensity, which is number of operations per bytes you fetch. Well, I know a lot of you guys know a lot more about this than I do, but so it's going to be very easy for you to understand, most probably. So this measures how much data reuse a program exhibits. And basically, long story short, thousand brain systems have low operational intensity. And that's for two reasons. The first one is there's this autoregressive loop, so you cannot batch over steps. But there's a second reason that makes a lot of sense when you think about it, which is that these systems are basically a set of heterogeneous weights that operate on heterogeneous inputs. So there's not really a lot of reuse that can happen within all this. So this is the performance plot of some very popular AI accelerators. So NVIDIA GPUs, Google TPUs, compared to their operational intensity. It's a roofline plot. And what I want to highlight is that where GPUs thrive is really in this high operational intensity area here. And they really struggle. They have low performance in this low operational intensity area. And coincidentally, you have deep learning systems which exhibit very high operational intensity because they batch heavily in their kernels. And you can see that almost over time, they more and more aggressively are operationally intense. And you see that Montyll and Montyll are very low in operational intensity. And so within GPUs are not a good fit to scale up thousand brain systems. So now CPU, well, the basic idea behind scaling these models on CPU is very easy, right? You just kind of put the learning modules in different cores, for example. And here, the one thing that I want to highlight is the data movement. So what we're gonna try to figure out is within this whole setup here, where you get a patch, you get the feature and a pose through the sensor model, you get the object ID through the learning module, and then you get the movement through the motor system. You really wonder how much data do you use to generate all of these things. And it turns out that when you scale up, like for example, to the size of a cat cortex, which is 2,500 learning modules, you have about, let's say about like 100 gigabytes that you need to fetch per step. And so the question is, can multiple CPUs handle this data movement? And so you have this setup basically, with memory and logic separated. And you have, well, we assume well enough memory to fit the whole model. But the on-chip caches are overwhelmed. So you need to fetch data from the main memory. And here you're kind of doing well because you have a large enough bandwidth to main memory, and you have very high performance prefetchers that can hide the memory latencies. And so CPUs are a good candidate to scale up 1,000-brain systems. Now, our last candidate is a processing memory. And these are systems that kind of contrast with the traditional von Neumann architecture, where you have processing and memory separate, and that communicate through a narrow bus. In processing memory, you try to place cores or logic elements very close to the DRAM cells. And the idea behind this for our application is that, well, on the left, with a von Neumann architecture, you need to stream this 100 gigabytes per step. And on the right here, it seems more manageable. You only need to really move 50 megabytes per processing memory core per step. And so, the idea is that, well, then you can really compute the response from all of these models in parallel using, 2,000 processing memory cores, for example. And the idea is that, well, you have the system, and just like for CPUs, you kind of put them in different cores. And yeah, I mean, if you manage to put one core per one learning module per core, it enables you to scale to a cat cortex with basically the same time that it would take you to just compute one learning module response. So it's a good candidate for scaling up 1,000-brain systems. A small aside on data centers and compute clusters, because I mean, this is a lab that is extremely good, one of the best in the world at this type of stuff. So I think it's really interesting and relevant to scale up 1,000-brain systems to these kind of data center scale machines. And unfortunately, we only focus on single node performance in this work. And one of the reasons we do so is also because of this interactive environment here. Because unless your environment is virtualized, in which case data centers could work really well, you have this real-time processing constraint, which could be a real challenge for data center scale machines. So now we can finally talk about our novel 1,000-brain systems, which is called Montyll. And what really changes in Montyll is not all that much. It's a classic 1,000-brain system. It just is implementing those learning modules differently. So instead of having explicit graphs in 3D space, we basically use accurate neuron models to do similar things. And we're going to see what this means. So the design principles that I go after for designing these learning modules is really the cortical column here. And the reason why I can do that is because it turns out that the cortical column, the layers in the cortical columns, can really be attributed functions, specific functions. Like, for example, in layer 3 or layer 4, it's responsible for representing the location, or the feature. Layer 6 is responsible for the location. Layer 3 is responsible for the object ID, for representing it. And so I'm kind of following this logic here in the learning module, where I have a location layer, feature layer, and an output layer. And how I implement these is basically with these networks called hierarchical temporal memory networks, HTM. And what these are basically a bunch of neurons. And so you might ask, well, if this is just a network with a bunch of neurons, how is it so different than traditional neural networks? And to really answer this question, give an idea, I gotta show you this about action potentials. This is the classic way that neurons spike. They have this action potential, and they just emit an action potential down their axon. And this is basically the thing that traditional neural networks are designed after. In the 90s, there's a new type of spike that was discovered called the NMDA spike. And the very weird thing about it is that it depolarizes the cell just enough to not cause a spike. So it does something, but it doesn't cause a spike in outputs. And so the scientists were kind of curious about this and wondering why it existed, because they couldn't attribute a function to it. And the very interesting thing about it is that the initiation sites at which that cause an NMDA spikes, they account for like 90% of the connections in the brain. So not explaining this means you haven't explained 90% of the connections in the brain. But in 2016, there was a proposal for how these NMDA spikes could actually represent prediction. And to explain this, I'm just going to show you this. Imagine you're a runner and you're the only one. You go at 1, 2, 3, go. And imagine you're the only one to hear the 1, 2, 3. And the others do not. They don't have no idea. It kind of puts you in a prime state, which means that as soon as you hear go, you're primed and you go way faster than the other ones. And actually you go so fast that the other ones kind of don't even try. They're like, oh, he's so far in advance. And that's actually called inhibition in the brain. And so this predictive state is one of the basic mechanisms behind these HTM networks. And there's been a lot of work on them basically over the years. And what I'm doing is basically putting a lot of these works together into a single layer. And so I have a unified mathematical formulation, which you'll have to basically read the thesis because yeah, I don't have time to explain this, I guess. So I have a bunch of activation and learning rules here for the network, algorithmic and space complexity. And that kind of leads me to the implementation, which, well, maybe I expect this to be the part that interests people the most. I don't know. But basically, we implement Montyll in C so that it's amenable to system studies, basically. And this library that we implement basically serves as the backbone to both of our CPU and processing memory implementations. And today, I'm not going to talk about the CPU implementation much. It's very similar to the processing implementation. And the reason why I won't talk about it is because the design decisions that we made for this library are best understood under the light of the challenges we faced implementing on this processing memory system. So to go back a little bit, processing in memory. The promise is this: computing all this in parallel. That's great. What's the catch? Well, the catch is there. The cores are very weak. They're very low frequency, 400 megahertz. And the internal bandwidth, although in aggregate is massive, just for one core is actually pretty small. And so this is the processing in memory architecture that we use. And to really go further into the limitations here, you have to play with cores that can only do 32-bit integer arithmetic, no floating point, only 8-bit integer multiplication. And you have to kind of explicitly manage all the accesses from your core to the memory through like a scratchpad memory, which is kind of like a cache, but it doesn't function as a cache. You need to manage it yourself, whereas the cache does it for you. The interesting thing about our network here is that a lot of these learning and activation roles really play well into the limitations of these cores, actually. They're really simple operations, very simple arithmetic logic operations, except maybe one exception. There's one exception that I'm going to talk about. So first thing that we did to optimize this implementation here. So you have this scratchpad memory, which is 64 kilobytes. And you're going to want to fit all the states of your network within this scratchpad memory. The reason why is because this is the only way you're going to get a single cycle latency to these states. And you use these states aggressively when you compute responses of these models. So while you can stream the weights, you can't stream these from a different memory. And well, the states are activation and prediction. So each neuron can be in an active or a predictive state. And this is why. And so what we do is that we basically pack them in 32-bit integers and we access them through bit serial computation. Now, the other thing is we got to fit all the connections into this bigger bank, this MRAM, that we stream into the scratchpad memory. And so these matrices are highly sparse, and basically we compress them using a sparse representation, and we managed to basically pack each entry into a 32-bit structure, which stores both the incident cell index and the permanence, which is kind of like how potent the connection is. And this is enough information to determine what the connection does and how strong it is. Now, this is the big outlier here, this operation, this boosting operation that happens at some point. Well, you recognize that this is a pretty floating point intense operation here with an exponential value and all that. But there's no floating point unit. So what do? So we basically implement these boosting factors using a combination of fixed point arithmetic, and we use these thing called hybrid dynamic precision lookup tables to basically keep the boosting factors very close to their value, no matter what the input statistic might be. So to transfer all the connections, to stream the connections from this big bank memory to the scratchpad memory, we basically use blocks of 2 kilobytes. It's basically the blocks that enable you to have the maximal transfer bandwidth. And what it kind of looks like is that you basically have this big connection matrix here, which is an MRAM, and you basically stream it with these private buffers. And we'll see why it's called private buffers and there's so many tasklets next to it. Tasklets are just like threads, actually. And this brings us to my next point, which is that it's another limitation, actually, of these cores, because you have to work with this pipeline, basically, which is fine-grained multi-threaded. I don't know if you've ever heard about it. Before working on this, I didn't hear about it. And it's basically some kind of a pipeline where no two instructions from the same thread can be scheduled at once. So it means that you need to parallelize the work enough so that your pipeline will be filled. And this is kind of what we managed to do. And it turns out you can just assign a set of cells, a set of neurons to each tasklet, for which each tasklet compute the activation, prediction, and learning rules. And the last thing you need to do, since we parallelized, inside the cores, we also need to synchronize and have barriers, because you don't want a state that is not settled to be used in a computation that needs it after, right? You need the threads to kind of stop at some point and stop computing before everyone is done with the previous step, basically. And so all these arrows represent barriers. So our methodology here, we basically use 3 systems, one with not too many cores, 12 cores, the other with 48 cores, and this processing memory system with 2,560 cores. They're called DPUs there. And for the processing memory system, we used a cycle level simulator called UPemulator with this following parameters. And we also test our implementation using the optimum functional simulator. And here are basically the results here. So basically, as far as scaling goes, we successfully scale Montyll to 2,560 learning modules on this high-end CPU and processing memory, which kind of represents 44.5 billion neurons and 16.1 billion synapses. This is kind of like the scale of this guy, guinea pig. And this is a graph of the runtime per step as the number of learning module grows. And you'll see here that as you increase the work, the number of learning modules you need to compute, the CPU takes longer and longer because you need to do more work. And the processing memory, you don't really have this up to the capacity of the processing memory system, of course. And so we found that the processing memory implementation outperforms the high-end CPU by 2.x for 2,560 learning modules, with 2.55 steps per second versus 1.14 steps per second. And the interesting thing is that the CPU, the high-end CPU, it kind of benefits from higher instructions per cycle as the number of LM increases, which kind of explains this sublinear scaling we have at the top. Now we really see the weakness of these processing and memory cores here, because with the performance on a single core, on a single learning module, because both CPU completely outperform it by 32x and 84x. And we have other results in the thesis. So in conclusion, we've shown the scaling requirements from these 1,000 brain systems. We basically implemented a novel 1,000 brain system called Montyll, which uses these hierarchical temporal memory networks, for which we kind of provided a unified mathematical formulation that unifies previous works into a single layer. And we provided this implementation of Montyll on a processing and memory system. And we successfully scaled Montyll to 2,560 learning modules on a CPU system and a processing memory system for a total of 44 million neurons and 16 billion synapses. And the processing memory system outperforms the CPU system by 2.2x. And we open source our code right there. And that is it for me. Thank you. Do we have a...
Yeah, do we have any questions?
Do you have any question? Oh,
Go ahead.
Yeah. So I have a question. So you mentioned that GPUs don't really perform well on the memory bound regime, but I mean GPUs come equipped with an HBM memory and they actually provide more. I mean, from any CPU you can buy, they will provide more bandwidth. Is it like why did you like? Is it really the case that the CPU implementations are more efficient than the GPU implementations, or did you just want to focus on the PIM implementation?
Well, it might have a very big bandwidth to memory. It's a very good point, actually. I've thought about it for a while. So it makes a lot of sense to think about this. What I found is basically there's two things. The first thing is that to really utilize this bandwidth, you need to have very high operational intensity. You need to have a lot of parallelism and a lot of reuse that you don't really have in these. But maybe you can tell me otherwise. I'm not a professional, and you know a lot more about GPUs than me. But the second thing, which is very interesting, is that when you look at the operations that are done, they're very hard to batch, actually, and really hard to even implement on the GPUs themselves. There's a lot of branching conditions and stuff that GPUs are not really great at. Like when you look at Montyll, the implementation from 2024, this one basically at some point spends maybe half of its runtime doing this thing called a KNN search in a tree. And this is basically pointer chasing with branching everywhere. And that's, well, pretty terrible for GPU implementation, I believe.
Other questions?
I'm curious about one of the first slides where you had some visualization for the cup and the point, whether it's in the cup or not. Is that just a visualization or is that part of the system itself? So if you go back to like one of the first.
So this is like this, for example, this thing?
No, go. These visualizations.
So this is not my system. This is just an example of an existing thousand brain system and how it really does 3D object recognition.
Okay. And what does the evidence represent here? Is it like what the model is seeing or something like that?
Yeah. So basically the evidence is what the model thinks it's seeing. Yeah. So for example, here, this at step 0, it knows nothing about anything. It just receives dispatch. It doesn't know anything about anything else. And so it kind of goes through all the models and it thinks like, okay, what model, what object could this be?
But isn't it reversed? Because you think that it would know more at step 30, so it would have a better image of the mugs? Because it seems like it's.
Oh, that's a really great point. So
step 0 is perfect.
Exactly. No, that's a really great point. Actually, if you really look, step 0 is very uncertain. Every point has an equal evidence, basically. Like this, basically what this means is that the model doesn't know where it is. It doesn't know what it's seeing. It's kind of thinking like everything could be a good candidate for this observation. Whereas in step 30, there's only one specific point that is high evidence and the rest isn't. So it's sure about what it's seeing. And so it's sure about what it's not seeing also.
I see. Okay. So I read this in the opposite sense, in the sense that the model is not creating the visualizations. It's given the probability on where the point is within this object, I guess.
Yeah.
And so in the lower images, it's higher on a specific. Okay.
Yeah.
That makes sense.
I took me a long time to understand this as well. So
yeah.
Yeah.
I have a similar question to the one for GPUs, like also specifically for CPUs, because this PIM is better than CPUs, but if you look at the plots, like the advantage over CPU is kind of 2x and really flattens out.
Yeah.
Now, okay, we don't really have PIM working. I mean, we do have some prototypes, but like still a long way. Why not just focus on even CPUs and to a bit more, be smart about how we should implement this and just run it there.
Yeah. Well, that's a good point. I think that's a good point. It kind of makes sense. I mean, the thing is that what you're saying is basically processing memory, it's so hard to make it work, and it's not commercial, it's not available. Like, why go through all the troubles when you have 2x over like a weak baseline, basically? And yeah, I think you're totally right. I think one thing I will say is that CPU definitely represents maybe the best commercially available system to scale 1,000 brain systems. But I will say that I do believe that processing memory is an interesting path forward. Like, it could really enable like future scaling, let's say. But I also have other thoughts about enabling future scaling that doesn't really necessarily rely on processing memory, nor or DRAM-based processing memory, nor CPU, actually. But yeah, I agree with you 100%, Mathieu. CPU is a great system to scale these models. This work was really about investigating all that. This is why I went to all the trouble.
Any questions from the audience on Zoom? Nope. Okay, so thanks a lot for the attention, and yep, congrats.
Yeah, thanks for everyone for I'm honored that everyone has come on Zoom and here in person. Thanks a lot.